Hi, I'm Chen Ronghan from Shenyang Institute of Automation, Chinese Academy of Sciences. Here, I'll present a new unsupervised deformation learning method. Given two shapes, our main goal is to deform the source shape to align with the target shape to find the correspondences. This technique can be used in many areas, such as texture transfer for animation and single view reconstruction for AR. Former methods usually represent the deformation as a per-point translation, which let the shape deforms too freely and may lead to artifacts. So they usually require strong supervision provided by ground truth correspondences. Moreover, they represent target shape with a single global feature vector, which is not enough to capture fine-grained geometric details. Our work solves above problem by introducing a coarse deformation graph and using local features for deformation prediction. As a result, our method can generate more accurate and natural deformations. First, let me introduce the deformation graph, which is inspired by a classic embedded deformation technique. Given a shape, the deformation graph is generated by downsampling operation. And deformations are parameterized by assigning each node with an affine transformation. This allows our network to learn natural deformation even when there are no annotations. Given a pair of input meshes, we first generate the deformation graph and extract local features via a pair of Siamese mesh encoder. Then, deformations parameters of the source deformation graph are predicted to deform the source shape. Finally, losses between the deformed shape and the target shape are calculated. Now, let's look at how we predict deformations for local features. First, I want to claim that this is actually a non-trivial task. In the extrinsic feature space, corresponding parts can locate apart from each other due to large deformation. Thus, they cannot be matched to predict deformation. We address the problem by proposing an extrinsic-intrinsic autoencoder to implicitly model a shared canonical shape where corresponding points share the same intrinsic coordinates. Then, we can use the canonical shape as a mediate to build connections between the corresponding features. Specifically, the intrinsic encoder first encodes source features into intrinsic coordinates, which are then decoded to synthesize corresponding target features. A MMD loss is further applied to mitigate the distribution divergence between the synthesized and original features. One procedure in embedded deformation is to assign controlling nodes to vertices on source shape. If you implement this with naive KNN search, artifacts will emerge, while our full results are much smoother. This is because Euclidean neighbors don't consider mesh topology. For example, the nodes on the arm are wrongly assigned to vertices on the rib. Thus, lifting the arm also brings the ribs up. To solve the problem, let's first recall how the deformation graph is generated. We apply the Grackless algorithm, which aggregates a cluster of vertices Ci into a node Gi via edge contraction. Thus it guarantees Gi is neighbor of Ci topologically. During deformation, we trace back to find Ci for each Gi and regard Gi as Ci's controlling node. Then we further propagate in the deformation graph to define other controlling nodes for vertices in Ci. We first show results on less sufficient training data. Comparing to former supervised methods, our unsupervised method still shows lower error while avoiding artifacts. On public Faust benchmark, our method outperforms SOTA unsupervised methods by 24% on the inter-challenge and even supervised methods by 13% on intra-challenge. Here we visualized the canonical shape. We can see that it looks like a human skeleton. And it presents consist shape, though input shapes are highly different. The canonical shape can also allow us to directly build correspondences. Finally, our network can also learn a compact latent space, which allows it to be used for several applications, such as shape interpolation and human pose transfer, where we can transfer the poses of the source shape on the left to target shapes on the right. For more details, please check out our paper and supplementary material. Thanks for your attention.